Okay, there will be a little bit more in part 4 that I will cover, and we'll proceed with part 5 thermodynamics. Okay, so in part 4, I would like you to have a look at the slides that I have covered so far. Let me project the screen. Okay, so what we're looking at part 4 is actually the energy analysis for a closed system. Okay, before we proceed to control volume, hari ini kita akan tengok on the lecture of the control volume. But what we have covered earlier last Monday is on the closed system, right? So I would like you to get through to the slides for the next 2 minutes, and then try to browse through until and look carefully on it. Okay, on the slides itself. And then I would like you to actually go to menti.com, and there is a code over there, 18674424. I would like you to actually share with me which particular slide that you still have challenge to understand. Okay, so have a look at the slides again. We stop until the specific heat capacity tu. Dekat heat capacity tu kita tak cover lagi. I will cover right after this. But from slide 1 until slide before the heat capacity slide tu, which particular example ataupun slides that you face challenge to understand? So kindly please respond to this menti.com 18674424. Let me share screen again. Okay, you can go to menti.com 18674424. Please share with me which part of the slides that you have difficulty to discover, to understand. Okay. I noticed that most of you have, I think majority of you who have responded here has some difficulty on the energy balance for closed system. Okay. By the way, I have already uploaded the previous recorded lecture dekat YouTube. Okay, so you can find it over there. I'm not going to actually give a lecture back on uh, whatever it is that we have covered earlier lah kan. Alright. But some of you ask again that even polytropic process is something that actually I have actually explained last Monday. So try to have a look back at the recorded lecture and it should try to understand that. Most importantly, okay, as I said, as I keep repeating again and again, whatever that I give in my lecture is only one source of your learning. Okay, whatever things that you have discovered, for example, like you do not understand what is polytropic process, for example. So try to find information more from the books, textbook. Even you can Google right now. You can actually find information about what is polytropic process. Okay, so it is like what I'm giving you here for you is actually for you to trigger. Okay, something that makes you confused, then you need to clear it out. And it's not only the resources does not come only from me as your lecturer. I am here to facilitate that. Okay, these are the things that you need to know. These are the things that you need to cover, for example. And you are required, actually, you as a student, it is your responsibility to look into the information that is needed and try to complete the puzzle. So that is a task when you come into the learning process. As I keep mentioned daripada week 1, I'm not going to spoon feed you, right? So I'm going to actually facilitate you to make sure that, okay, what you are learning right now, okay, what are the things, what are the keywords. So try, if you do not understand about these particular keywords, then try to figure it out, try to understand more. There are also a lot of YouTube contents and you can also find information about it. Right? Okay. So for energy balance, okay, energy balance ni is a little bit that you need to know about this because when we move to part 5 later, kejap lagi, I'm going to talk as well about energy balance for open system. So kalau you tak clear on the closed system, um, it will be much more challenging if let's say we start to go for the open system. But never mind. Right? So let's have a look at little bit, just recap on energy balance for closed system. Kenapa kita nak buat energy balance ni? That's, I think, the first question that you have to trigger. Why do we need to do energy balance in the first place? Because in order for us to make sure that there is no we want to study the efficiency of the device. Anything, for example, if you design, if you later on, if you become an engineer, designing aircon ataupun designing hair dryer ataupun kettle, whatever it is that you are designing, for example, or you want to come up with a new product, and first thing first that you need to know about the energy efficiency. Okay, energy efficiency, for example, like how much energy that is going waste away from it, how much the energy is, for example, like from the electrical punya sources kan. Katalah kita buat hair dryer, imagine a hair dryer, and you plug in that hair dryer dekat electrical sources. Do you believe that 100% of that electrical energy itu will be transferred to the appliances, ataupun there will also be some other energy that is being released out? For example, like if you imagine about hair dryer, of course there will be some heat being generated, right? So does all the heat generated to go straight to your hair, ataupun sebenarnya there will be some heat is released out to the surrounding? So if you want to know about the heat release, how much is really heat release out to the surrounding, whether you are making an efficient punya kind of equipment, this is where actually we study energy balance. Okay, energy balance for procedure, because you know that energy cannot be created or it cannot be destroyed, but energy will be transferred from one form to another form. So what we talk about last Monday about closed system ni means maksudnya kalau satu sistem tu yang there is no mass transfer. because there is, when it is a closed system, you have a bottle, for example. Okay, you have a bottle. This is closed, and when it is closed, which means that there is no mass can leave the system. Okay, only what happens is that there can only be heat come in and go out. Okay, from the system. So this is one of the example of closed system. But once you start to open it, for example, okay, and then there will be some, for example, like the liquid inside here can be vaporized, and it can just go out to the surrounding. So this is considered no longer as closed system. This is an open system. So the part of open system we'll cover today. But for closed system, they'll be on heat being transferred in and out. Because when we talk about the open system, it's not only that mass being transferred in and out from the system, but it is also uh, there are also some kind of energy that comes together with the mass that I'll be sharing with you shortly. Okay, so in the closed system, it is much easier for us to do the energy balance because the term that is left with us is only is mostly is just a change of, for example, change of internal energy. Okay, there is a heat transfer in, and then there is a heat transfer out, and then there is affecting the change of internal energy. Imagine something like this. You have a potato. Okay, kita ada potato. Okay, that particular potato, kentang, kita masukkan dalam microwave. Okay, we put in the microwave. So what we did is actually we provide the heat from the microwave, the energy from the microwave enter the potato itself. Okay, and then for a while, after 1 minute, then you take out, you feel that the potato is being heated. It's already hot compared to the previous 1 minute. But at the same time, you should know that when you provide the heat to that particular potato, there will also some heat being released out from that potato. Okay, and that potato itself is a closed system because they are solid, intact. There is no mass leaving from that. So heat being provided to the potato getting hot, but at the same time there will be heat being released out from the potato. Sebab apa? After for a while, you can start to see that the potato is no longer hot, it's getting back colder because there will be some heat released out from the potato. Okay, if let's say there is no heating, if let's say kalau potato tu tak panas, it means that whatever that you transfer into the potato, it straight away it left out the potato itself. So this is where actually energy balance comes in. Energy balance ni ialah di mana kalau kita sebut pasal potato tadi, energy in is energy that is being transferred to the potato. Energy out is the energy that is released out from the potato itself. So if let's say the potato is still hot, this is where actually the change of energy happens inside there. Okay, so there is a heat coming in, there is a heat going out, or there, for example, or there can be work going out from that, but there is also something that is remaining inside there. Okay, this is what we call as the change of energy within that system. Okay, whereby that if this is a closed system, whatever that is changing inside there is what we call as change of internal energy, kinetic potential, and so on. So that is actually the purpose of why we're doing the energy balance. So when we do the energy balance, right? When we did this is the general analysis. So from here, we actually be able to derive our own equation. For example, energy in minus energy out is simply the heat Q in minus the work out. Okay, and the change of energy in the system, if you imagine the potato, it's only the change of internal energy. It can also be the change of kinetic energy and potential energy, but this is equals to 0 because it is a closed system. So there is no movement. There is no mass transfer. So kinetic energy is equals to 0. The change of potential energy equals to 0. So it just affects the internal energy of that particular potato itself. Okay. So this is just a further simplification of how they derive further from here. Okay. For example, the work itself, it comes with two types of work. There ada satu moving boundary work. There is another one is other works such as shaft work, stereo work, and so on. Okay, so that is all about energy balance that I would like to share with you on the closed system. I would like you to actually revisit the recorded lecture. I would like you to go to the textbook. I would like you to go to Google, find in the Wikipedia and so on, find more information about this. Right? So we're going to move into specific heat. What is actually specific heat? Okay, specific heat ni and why it is important? Because later when we're talking about the moving control volume whatsoever, the specific heat is also playing important role that we should know. So what is specific heat? Dia ada dua type. There are two types of specific heat. One is actually at constant volume. Another one is specific heat at constant pressure. Okay, two specific heats. Okay, what is the difference between specific heat at constant volume and specific heat at constant pressure? Okay, specific heat at constant volume ni, the definition of it is actually the definition of specific heat of at constant volume is actually the energy required to raise the temperature of the unit mass of a substance by 1 degree as the volume is maintained constant. So for example, you have a rigid tank. Okay, you have a rigid tank. Okay, the volume here is a constant. The volume here is a constant. And then you have a mass within the volume itself is 1 kilogram of mass. And then there is a change of temperature of 1 degree Celsius. Maksudnya perubahan, katalah this particular tank, rigid tank, the punya temperature initially is 36 degrees Celsius. It's being heat up to 37 degrees Celsius. So there is a change of temperature of 1 degree Celsius. And that particular volume is constant and the mass of that object is 1 kilogram. So, in order for us to change kita nak panaskan daripada 36 ke 37 degree tadi, okay, we need some kind of energy. Okay, energy required to raise the temperature of the unit mass to 1 degree if the volume is maintained. So that amount is fixed, and this is what we call as specific heat at constant volume. And the amount is 3.12 kilojoule per kilogram degree Celsius. So, kalaulah kita ada satu, okay, if let's say I have this water bottle, so this particular water bottle is a fixed volume, it's a constant volume, right? The volume will not change. And I have water fully filled inside this of 1 kilogram water. And the temperature right now, because it's a bit colder, is 25 degrees Celsius. And I want to raise the temperature to 26 degrees Celsius. So in order for me to raise to the temperature of 26 degrees Celsius, I just need 3.12 kilojoule so that it becomes 26 degrees Celsius. So how I could do that? Maybe I can just supply some kind of energy from my hand. Okay, I can do some kind of shaking so that it is equivalent to 3.12 kilojoule and it will raise up the temperature by 1 degree Celsius. So that is specific heat at constant volume. But, okay, there is also another specific heat which is we call as specific heat at constant pressure, CP. CP ni is energy required to raise the temperature of the unit mass of a substance by 1 degree as the pressure is maintained constant. So this is always what we talk about gases, for example. Kan? So imagine a piston, something like this, and kalau the piston is not moving, which means that the pressure is changing. Okay, kalau kita ada gas dalam ni, imagine there is a gas, right? And then when you heat it up, the gas will actually start to move. Molecule inside the gas become when they start to collide with the container wall, in order for us to make sure that the pressure does not increase, okay, this particular piston should be movable in a way that it's once the heat is there is some heat, and the piston, it will start move so that it allows the molecule of the gas behave as usual. Okay, supaya dia tak melanggar each other, because once they start to collide with each other, they start to collide with, then that's where actually dia angkat increase the pressure. But right now, okay, kita movekan piston tu. The piston tu is movable. Okay, imagine kalau macam ni lah. Again, I use the elevator punya analogy. Kalau kita ramai-ramai, okay, if let's have 5% inside an elevator, okay, so that particularly 5%. So the lift tu might be dah start nak cramp, tapi everybody have their own space with each other. But katalah masuk lagi 5 orang dalam lift tu, then everybody start to feel tight. Okay, when they start to feel tight, the pressure is already increasing. Okay, the pressure is already increasing. But you don't want to do that. So what you can do is actually you expand the lift a bit bigger. Okay, so that you still feel the same pressure. So you want it to be a constant pressure. So if you want to raise the temperature at a constant pressure by 1 degree Celsius, okay, so you need 5.19 kilojoule per kilogram degree Celsius. And this is a fixed amount, okay, by 1 degree Celsius of a mass of 1 kilogram lah. Maksudnya kalau you punya mass dah jadi 10 kilogram ataupun mass dah jadi 100 kilogram, then you need more energy lah in order for you to raise up the temperature by 1 degree Celsius. So that is what it means by specific heat at constant volume and specific heat at constant pressure. Okay. So the equation in the figure are valid for any substance undergoing any process. So CV and CP are considered as properties. And CV ni, specific heat capacity for the volume, is related to internal energy, and CP is actually related to enthalpy. And the common unit tu is ni lah, kilojoule per kilogram per degree Celsius or kilojoule per kilogram Kelvin. So if the units are identical, of course, because it's the same degree difference, because it's just change of temperature. Whether it is in Celsius or whether it is in Kelvin, it's the same degree, it's the same magnitude. Right. So here, the specific heat of a substance, okay, it changes with temperature. So kalau macam ni, kalau kita kata, okay, if you look at the CV ni is actually the change of internal energy with respect to temperature at constant volume. Okay, so this is actually the definition of CV, and the DCP itself is actually delta H divided by delta T at constant pressure. Okay, enthalpy, change of enthalpy with temperature at constant pressure. So the internal energy, enthalpy, and specific heats of ideal gas, right? So if let's say you are looking at this particular equipment, okay, and you have a high pressure, high pressure, and then you have a valve, and this particular air, okay, it's like a balloon inside the water, and you have a thermometer. So this is actually schematic experimental apparatus used by Joule, okay. So that is why actually yang kita dapat apa kilojoule apa semua tu kan. This is this setting of experimental work. So that this is why actually they measure the energy. Okay. So whenever that we have we want to see the relationship between internal energy, enthalpy, and specific heats for ideal gases. Okay. So if you can remember, the enthalpy punya unit is actually H equals to U plus PV. Specific enthalpy equals to specific internal energy plus with the pressure versus with the specific volume. And then the PV is also equals to RT. So this is the ideal gas equation. So if you be able to get specific enthalpy is equals to U plus RT. Okay, U plus RT. And U is equals to and U is a function of temperature. Okay, it's a function of temperature. Enthalpy is also the function of the temperature. So if you differentiate it, du is equals to Cv to the power of temperature, right? And dH is equals to Cp. Cp in the function, you integrate the Cp, the function of temperature. So the change of internal energy, U2 minus U1 is actually the integration between state number 1 to state number 2 of Cvt dt. So this will give you the change of internal energy, and change of enthalpy is actually CPT dt. Okay, so you will use a lot of these terms later when you are using you're doing energy balance. Okay, so internal energy and enthalpy change from an ideal gas is actually they are changing. Maksudnya you can actually determine the change of internal energy and change of temperature from the Cp and Cv value by integrating it. Kejap eh. Okay. We look at this particular slide, which is actually looking at the relationship between the Cp and Cv. Okay, between the Cp and Cv, we know that enthalpy is actually related to U plus RT, because we look from here when we combine these particular terms, then be able to get enthalpy equals to U plus RT, and the change of enthalpy is equals to change of internal energy plus R dt. Okay, this is where actually we further, if let's say there is a change of enthalpy, it's also change the internal energy with respect to temperature changing. R is gas constant, so R maintained as it is. So if you rearrange back, if you look at the previous term, du is Cv dt and dH is Cp dt. So when we put inside the term, dH is actually Cp dt and du is equals to Cv dt. Kejap San, move away San. Gegar meja. Okay. So when dH is equals to Cp dt and du is equals to Cv dt, this is from the term that you can see from here. Saya tak tahulah kenapa dia punya mouse ni sensitif sangat. So Cv dt and Cp dt with respect to du and dH. So kita masukkan dekat sini. dH is equals to Cp dt and du is equals to Cv dt. So when you rearrange back the equation, okay, you'll be able to get Cp is actually equals to Cv plus with the R. R is the gas constant. Okay, and when you rearrange back, and when you have this, is actually K is a specific heat ratio, Cp divided by Cv. You will be able to get K. So kalau K ni tadi, kan, you also be able to use it dalam polytropic punya calculation later. Okay, kalau kita tengok balik slide yang related to polytropic, then you be able to put the other requirement PV to power of K, which is respective to Cp over Cv. Okay. So Cp of an ideal gas can be determined from a knowledge of Cv and R, which means that kalau kita tahu Cv dan kita tahu R, then you be able to determine the Cp. Sama juga kalau kita tahu Cp dan of course kita tahu R, then you be able to determine the Cv value. So Cp and Cv are actually related to each other with this particular equation. Cp is equals to Cv plus R. Okay. Kalau incompressible substance macam mana? Contohnya macam liquids, macam water, macam solids, macam potato tadi contohnya. So this is what we call as incompressible substances. For incompressible substances, CV is actually equals to CP. Okay, dia ada heat capacity dia, which is equals to CV, also equals to CP. Right? The differences here for CP and CV is mainly difference because of the gas. But if let's say you are talking about solids and liquids, they are incompressible, and usually CV is equals to the CP. Okay. Looking at the internal energy changes, when we actually want to estimate the enthalpy, for example, internal energy changes, we can use CV to as because different material, different substances, different gases, for example, have a different CV value. Okay, when you have a CV value, once you get to know the CV value, then you'll be able to integrate those function. Okay, because dia akan datang dalam bentuk macam ni. Kalau dalam untuk CV ataupun CP, dia akan datang dalam bentuk macam ni. A plus B T macam itulah. Okay, plus CP square plus DP cube or something like that. Okay, CP ataupun CV dia ada dia punya correlation dia. So the A value, B value, C value and D value ni selalunya we can refer to a property table. Dia ada information dia where you can actually list down because different gas will have a different A, B, C and D value and so on. So what you have to do is whenever that you got this particular term, okay, CVDT ni, you'll be able to get this term, and then when you integrate that, then you are actually integrating this term. So when you are integrating this term, then it will be able to allow you to calculate what is the change of internal energy, okay, between two temperatures, for example. Okay, and similarly with enthalpy changes. So enthalpy changes ni, you have H equals to U plus PV, and then when you actually rearrange back the equation, you'll be able to get dH is equals to du VdP plus PdV. Okay, but the specific volume kat sini kosong, so maksudnya you akan dapat VdP. So du plus VdP. So delta H is equals to delta U V, which is a specific volume, multiplied with the change of the pressure. Because what happened here is that we are talking about when it is we're talking about CP. Remember about the piston. Okay. Remember about the piston, right? The volume is constant. Okay, and then the what is changing here is the pressure. Okay, the changing here is pressure. So you'll be able to get C average plus delta T plus B delta P. Okay. So for solids, the term B delta P is insignificant. Okay, and thus H delta H is equals to delta U equals to C average delta P. For liquids, there are two special cases, which is one is constant pressure process as in heaters. So delta P is equals to 0. And if you have a constant temperature process as in pumps, delta T equals to 0. So you'll be able to have this particular term. Okay. So this is just some kind of information for you. Tak apa, hadam dulu. Kalau tak faham, we can actually explore more, find more information about this. You will encounter these letters masa dalam material energy balance courses pun, you also be encountering this kind of information. Okay. So there are actually two problems that I would like you to have a look. I'm not going to discuss today. I would like you to do on your own. Try to figure it out based on the example calculation that has been done in the past. So you can try to resolve this question. Yang problem 2 nanti I will share with you the solutions. Okay, so this is actually the end of the chapter 4, and so that we shall actually move to chapter 5 punya slide. Okay, before that, do you have any question? If you have any question, you can write down dekat chat section. I try to address that. Okay, so in part 5, kalau dalam part 4, we are looking at closed system. In part 5, we are looking at what we call as control volume, which is related to open system. So it's no longer closed system. Before we start, we can take a break dulu lah, ambil masa 3 minit. I think 5 minutes until 11:48. Then we will shall continue balik. Okay, 5 minutes break. Okay. Before I start with the next slide, okay, I would like to ask you, what do you think will be the difference between part 4 and part 5 thermodynamics? Um, Part 4, we're talking about closed system. Part 5, we're talking about control volume. So what do you think will be the difference between this part 4 and part 5? Part 4 is the energy analysis of the closed system. Part 5, the title is energy analysis of the control volume. So try to guess about what do you think is the difference between these two chapters, these two parts. You can start to browse dulu the slides. Um, you can have a look at the slides that have been given to you, slide 4 and slide part 4 and part 5. Get to it, try to look at the difference, try to observe what do you think is significant or big changes dalam part 5 when compared to part 4. Okay, so far I got 6 response. You said open and closed system, energy transfer closed system do not have mass flow, open system have. Okay, existence of inlet and outlet. uh, okay, all right, you're almost there. Okay, so in part 5 we're talking about mass and energy analysis of control volumes. So before I proceed, I would like to ask you, please share an example of control volume around you. You don't have to give example about whatever that you have not seen before. Tak payah bagi example about turbine ke, diffuser ke, uh, but what is surrounding you. Share an example of control volume surrounding you. Nozzle is nozzle of what? Okay, water tank. Water tank is an example of control volume. That's good one. What else? Ada apa lagi example of a control volume? Water bottle is a closed system. Melainkan you buat ada inlet dengan outlet. A cup of coffee pun bolehlah consider control volume, tapi kena be a bit confusing kalau kita cakap tentang cup of coffee. So far water tank is a good example of control volume. What else? Shower head, okay. Pumps, okay. Think about a control volume punya surrounding you, whatever that you have at home. Ada kita ada water tank kan, watering can, uh, possible. Okay, try to think about something that have an inlet and outlet. Think about something yang macam kita ada water pipe, okay, dia ada control dekat situ. Of course water pipe kita is a control volume. Any example? Any more example that you can think of? Heat exchanger in car, which is the radiator, the car radiator. Yes, that could be a control volume. A car engine, air conditioner, okay. Air conditioner is a control volume system. Hydraulic brake, okay. Nozzle and diffuser ni korang ni potong steam lah. Mesti tengok slide, ambil jawapan kat slide. Tak kreatif langsung lah. Cuba fikir something else. Cuba fikir luar slide sikit. Apa benda lagi selain ni? Apa benda lagi yang boleh? Dynamo. What is dynamo? Okay, dynamo for the bicycle. Stable water kat. Boleh tak mute siapa yang cakap tu? Okay, what else? What else? What are other things? Try to think further. Be more creative. Try to think surrounding you, just surrounding you. What is actually example of control volume? Air diffuser. Okay. Washing machine. Washing machine. Air cooler. Okay. Kettle, microwave oven. Okay. Balloon. Okay. Balloon can be a control volume. Yeah, you blow in it and then lepas tu dia akan sip out from the balloon punya pores tu. Power bank. Power bank can be a control volume. Yes. Boleh. Power bank. Why not kan? Water dispenser. Water filter. Okay. Right. Phone. Phone charging in, charging out, using out, heat dissipate out. Yes, iPhone, phone, mobile phone can be used as well. Okay, thank you. So let's have a look at the slide. So now we're going to talk about the mass and energy analysis of control volume. Tadi kalau dalam part 4 kita tak bercakap tentang mass. Kan? Kalau kita kata pasal mass in the closed system, we're not going to talk about mass because mass ni dia tak ada pergerakan. There is no mass transfer in a closed system. But when we talk about the control volumes, like you said, for example, like a water tank. Okay. Now I would like to just consider, let's talk about water tank lah. It's easier that you can imagine about water tank. There is something that is being transferred in the water. Okay. There is a mass transferred in the water. And then lepas tu, with that water, dia akan ada outlet juga. Okay. So within that tank is what we call as control volume kat situ. Okay. And then there is a flow in of mass in and mass out. There's also some energy in and energy out as well. Even though maybe we can consider a heated water tank to be another good example, because later when a heated water tank tu kita panaskan untuk dapatkan air panas kan. So that will be much more easier for you to recall about mass and energy analysis for this control volume. So for the learning outcome for this lecture, you are able to expected to develop the conservation of mass principle. We're going to apply the first law of thermodynamics as the statement of the conservation of energy principle to control volumes. We are able to identify the energy carried by a fluid stream crossing a control surface and blah 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 kat sini tak apa, so you don't have to worry about that. We're going to solve some energy relay balance problems using nozzles, compressors and so on. Okay. But first of all, other than energy, that we have to remember that another thing that cannot be created or destroyed is mass. Okay, so that's why kalau nanti belajar ialah tentang mass and energy balance, you will be learning in one courses we call as mass and energy balance. Why mass and energy balance? Because both of these, mass and energy, is actually, they are conserved property. They cannot be created nor be destroyed. Okay, because it's gonna be a balance term. So for example here, kalau kita tengok Einstein equation E equals to mc square. So E is related to M. The energy is related to mass. Okay, the energy is related to mass, and both of these properties are not be able to be created nor be destroyed. Okay. So for example, you are creating water. Katalah you have a technology to create water from hydrogen and oxygen, right? So you have a 2 kilogram of hydrogen, you add on with 16 kilogram of oxygen, then you'll be able to get 18 kilogram of water. So even during the chemical reaction, the mass is being conserved. So mass of system will change when its energy changes. So for closed system, mass of the system remain constant, but for control volume, mass can cross the boundaries, which is it is an open system. So the amount of mass flowing through a cross section per area is called mass flow rate. So let me draw. Kita go back to the water tank. Oh, you say ni. Okay, kita ada pipe. Katalah ada pipe connecting to the water tank, and then alright, so it carries some amount of mass of water flowing through the tank. Okay, and then there is an outlet from here pula untuk transfer ke somewhere else. Okay, so the amount of mass flowing through a cross section area per unit time is called mass flow rate. So kalau pipe ni, right, this particular pipe, there is what we call as a cross. Kalau kita potong tengah-tengah kat sini, kita akan nampak cross sectional area, okay, pipe of the pipe tu. So there is a mass going through this, which is the water going through this, is what we call as mass flow rate. This is the flow rate of the water that is coming through to this area, and we can measure that by simply calculating the density of the material itself, multiply with the volume average, multiply with the cross-sectional area A. And be able to get M is simply rho V dot. Rho V ni, rho is a density. Okay. V dot ni is actually the volumetric flow rate. And in order for us to determine that, also we can have volumetric flow rate divided by the specific volume, then be able to get mass flow rate. Okay. V average is the average fluid velocity normal to A. Rho is the density, A is the cross-sectional area normal to flow direction. In actual, kalau kita tahu sebenarnya, dalam flow ni, bila water lalu in a pipe, which is like this, water masuk dalam pipe ni, the flow dia akan jadi ada satu flow yang dekat tengah-tengah center tu, dia akan lagi ke depan kan, berbanding dengan flow yang sebelah tepi, because there is some friction at the wall of the tube. So the actual flow will look like this. Tapi what we are doing is actually we are estimating in a way that if we total up all the velocity of the water at different point, kita akan dapat an average punya condition lah. So that's why we have an average. This is what we call as average velocity. Okay, average fluid velocity. So actual and average velocity profile for flow in a pipe is the same for both cases lah. Okay. So if you want to determine the volumetric flow rate pula, volumetric flow rate is the integral of the cross-sectional area, different side of multiply with the V average of velocity. So we'll be able to get V average multiplied with AC, which is the cross-sectional area, and V times AC is actually we'll be able to get the volumetric flow rate. And as I mentioned earlier, the mass flow rate is actually equals to density multiplied with the volumetric flow rate, or the volumetric flow rate divided by V. Okay. So we look at an example. Air at 100 kilopascal, which is at 50 degrees Celsius, flows through a pipe with a volume flow rate of 40 meter cube per minute. Find the mass flow rate through the pipe. So this is about air, bukan air, air at 100 kPa, 50 degrees Celsius. So we know that PV is equals to RT. So when we arrange back this, we want to determine what will be the specific volume first. So assume air to be an ideal gas, and then we have R, which is equals to 0.287 kilojoule per kilogram Kelvin. This is a gas constant. Multiply with T is 50 plus 273 divided by 100 kPa. And when we simplify everything, then we'll be able to get the specific volume is 0.9270. And right now, you have a volumetric flow rate of 40 meter cube per minute. So 40 meter cube per minute divided by 0.9270, okay, which is the amount from here. And then 1 minute is changed into 60 seconds. Then you'll be able to get the mass flow rate is 0.719 kilogram per second. Okay. The conservation of mass principle, this is also a very important thing in a control volume. What happened here, okay, bila kita ada, katalah this is the bathtub, there will be some mass coming in, ataupun kita kata water tank tadi, the mass coming in, which is the water coming in into the bathtub. But at the same time, there's also some water leaving out. Okay, so when you have, if you want to try to balance it out, this is where actually it comes the equation. The total mass entering the control volume during a certain rate of time, delta T, okay, minus, okay, whatever that M in minus whatever that is M out is equals to net changes of mass within the CV during delta T. Is equals to whatever that is being left out here. So when you simplify the equation, M in minus M out equals to delta M CV. Kalau kita cuba relate balik dengan energy balance equation tadi, it looks the same, right? Kalau kita imagine balik potato tadi kan, case potato tadi, kita ada potato, energy being transferred in minus energy being transferred out is whatever the energy remain inside the potato itself. Sama lah dengan case kita buat mass conservation. M in minus M out equals to delta M CV. So delta M CV is equals to N final minus M initial. This is where actually after we rearrange back the equation, okay, and when we put the flow rate in the terms, okay, the mass flow rate in minus mass flow rate out is whatever that is being left here. Katalah there is no water left here, it is a continuous flow, so you should have actually M in minus M out equals to 0 lah, because there is nothing left. Tapi sekarang because ada bathtub dalam control volume ni ada water, there should be some amount left over here lah. But other than that, if let's say it is a smooth flow, this is 0, then you will have M in is equals to M out. So the total mass within the control volume, so if you have a control volume, the integral of CV P dV, okay, this is how you make the determine the mass, okay, and the rate of change of mass within the control volume, you put the term dmCV by dt, and then you integrate d over dt is of the CV of the density of the, and then with respect to dV. Sebab kita letak kat sini dV sebab and then density sebab kita tahu ada term density dekat sini. Term density ni related dengan volume and mass, and we have a general conservation of mass, d over dt integrate of p dV plus cs. Cs is the closed system, rho v with n dA equals to 0. Okay, so this is the general conservation of mass. Kalau kita buat dalam rate form, it will be equivalent to general conservation of mass in the rate form. dmCV over dt is actually the summation of mass in minus summation of mass out. Okay. So right now, we are looking at this particular system where actually you have 2 inlets and 1 outlets. So kalau kita buat material balance dalam control system ni, CV ni, you'll be able to get whatever that M1 dengan M2 plus M2 is actually equivalent kepada M3, which is the flow out kat sini. So this is the mass balance for steady flow process. Steady flow process, which means that the mass contained within a control volume does not change with time. So maksudnya dalam sistem ni, katalah kalau ada mass sekalipun, katalah kita ada dalam ni ada lebih kurang dalam 10 kg, it maintains at it is as 10 kg per second inside here. So dia tak berubah dengan masa. So what we can do is actually it shows that whatever that comes in from here should be equivalent to whatever that comes out from here. This is what we call as steady flow processes. So for a general steady flow system with multiple inlet and exits, it's actually equals to total mass entering CV per unit time equals to total mass leaving CV per unit time. Macam as I mentioned earlier lah, kalau contohnya kat sini, case tadi, katalah water tank ni, dalam water tank ni, dia amount dia maintain sahaja, maksudnya dia tak berubah, there is no change, ataupun is completely kosong, maksudnya whatever M in dia terus keluar, so you be able to have this, the change of the mass within the control volume system with respect to the time is actually equals to 0. Okay, it's equals to 0. So once you have that, then you'll be able to say that whenever that mass is entering in is the same as the total mass is going out. That is for the only valid for the steady flow process. So when we talk about the single stream of steady flow system, right now, if you agree back to this particular term, M1 is equals to M2, then we can just simply write whatever that comes in here should be equivalent to whatever that goes out here. Okay, M1 is equals to M2. And you'll be able to have this kind of relationship, rho 1 V1, which is actually from the mass. V1 is the velocity, A is the cross-sectional area, because V1 multiply with A1, then you'll be able to get your volume, and multiply with rho, then you'll be able to get total mass lah. So rho 1 V1 A1 is equals to rho 2 V2 A2. So many engineering devices such as nozzles, diffusers, turbines, compressors, and pumps involve a single stream, which is only one inlet and one outlet. So this is one inlet. This is turbine. Okay, so the function of turbine, they suck the air. So lepas tu turbine ni akan berpusing. Bila dia berpusing, dia akan generate electricity. And then this particular air, whenever that it comes in, it will lift back. Dia akan tinggalkan balik kat sini. But then it will have a different pressure. It might have a different temperature and so on. So control volume, it involves mass flow across their boundaries, and some work is required to push the mass into or out of the control volume. So kalau imagine kita ada sistem yang macam ni, okay, and then there is this is what we call as control volume, and there is a mass flow, which is there is mass coming in here, and then there is mass going out here. So in order for the mass to go out from here, there must be some work to push the mass in or out of the control volume. So the flow work, or we call it flow energy, is necessary to maintain continuous flow through a control volume. And the force applied to this is actually the pressure multiplied with the cross-sectional area. So you'll be able to get the flow work. Okay. So the workflow, kalau kita tengok tadi, kalau if you recall back dalam part 4, we're talking only about the moving boundary work, or additionally we can have a stirrer, shaft work, whatever. Dalam this part 5, there is a new term that is coming in, is what we call as flow work. Flow work ni is something that is necessary to push the flow going into the system and going into the system and going out from the system. So that's what we call as flow work ataupun flow energy. And the flow energy ni is defined by using this equation lah. Workflow equals to F multiplied with L, PAL equals to PV. Maksudnya P multiplied with the volume, pressure multiplied with the volume, you'll be able to get the workflow. And if it's a specific workflow per unit mass, then you just divide by mass lah. You will be able to get workflow is equals to pressure multiplied with the specific volume. Rehat kejap 2 minit. Saya akan stop actually today, hari ni dekat slide 19. I will further have some video for you to watch daripada slide 20 sampai habis lah. Okay. Sebab nanti kalau saya cakap banyak-banyak pun, I don't think that you'll be able to get what I'm trying to share with you. But what I will do is actually at least I will cover some fundamental punya parts and you have some idea about what is it all about. Okay. Cumanya kalau when people ask you, for example, like what's the difference between closed system and control volume, then you know what this is all about. Okay. Alright. So now let's have a look at the total energy of a flowing fluid. Tadi kita tengok pasal mass. Mass balance kan. Mass balance, whatever that comes in is actually equals to whatever that goes out. If let's say it's a steady flow process. So we want to do the energy analysis for this. So when we want to do the energy analysis of a flowing fluid, this is the term that is come in. Maksudnya kalau kita divide by per unit mass basis, E, okay, E is equals to U plus KE, which is the kinetic energy. This is all the specific, we call it specific energy for the simple compressible system is equals to the specific internal energy plus with the specific kinetic energy plus with the specific potential energy. Kinetic energy and potential energy can be calculated using this equation, V square, which is the velocity, okay, divided by 2 plus G multiplied with Z. Okay, Z is the distance and G is considered as the gravitational punya specific gravity. So for flowing fluid, an additional form of energy comes in, which is what we call as flow energy. So when we put here, when there is a system flowing, kalau dalam control system, control volume, there is a flowing fluid, okay, flow in, flow out. So we have to introduce this flow energy into the system. So when we write down in terms of the theta, we should add in PV kat sini. Where does the PV come from? PV come from here, which is the flow energy. So the flow energy add on kat sini, so PV plus U plus KE plus PE. And then, but then at the same time, we know that PV plus U is equals to enthalpy. So this reduced to this particular term. Okay. So PV plus E is actually equals to PV plus U KE PE kat sini. But PV plus U is equals to enthalpy. So you'll be able to get this particular term if we have a flowing energy. So if you remember, if we compare between the closed system as well as the open system, which is having a control volume, for example. So dekat sini kita tak ada term PV tadi. Okay, it's just this particular term. But for a flowing fluid, there is a flow energy coming in, and therefore, when you simplify it further, PV plus U is actually equals to specific enthalpy. So when you have an amount of energy transport, for example, like the energy from the mass, okay, from the mass itself, is just simply the mass, okay, multiply with theta, which is U multiply with M multiply with the term that you introduced earlier on this particular term. Then this is where actually you get the energy of the mass that is coming in. Okay. So the rate of energy transport, if let's say you want to calculate the energy rate, which is also equivalent to power, kilowatt, then they call it E dot, which is the mass flow rate of the system that is going into the system, multiply with theta, then you'll be able to get the rate of the energy transport. Okay. So, but also the terms that is what is actually happening here, the kinetic energy and potential energies of a fluid stream can also be negligible, okay, because this is the internal kinetic and potential energy. So you can have the E mass is equals to mH ataupun the volumetric flow rate of the mass is equals to m dot h. M dot h. So what you have to do is finally just multiply with the enthalpy changes, then you'll be able to get the energy. Kiranya macam ni lah. Kalau if let's say you have a system, a water tank tadi, okay, and then there is some water coming in here, alright. So in order for you to determine the energy that is coming in from the water is simply the rate of energy coming in from the water to the control volume is simply like the mass flow rate of the water multiply the enthalpy of that water at that particular temperature. So you'll be able to know what will be the amount of energy, rate of energy that is coming in into the water system. Okay. Let's have a look at slide 15. Let's revisit back on the closed system. Okay. Kalau kita buat closed system tadi, open system, kita bercakap balik tentang closed system. Closed system, we know that energy in minus energy out equals the change of the E of the system. And we know that from here, energy in minus energy out is actually Q in minus Q out plus W in minus W out equals to delta U plus delta KE plus delta PE. Where Q net in, okay, is actually Q in minus Q out, is the net heat input. W net out is W out minus W in, okay, work out and work done by the system. Work done to the system minus work done by the system is the net work output. So you have what we call as a cycle, okay. So in general, Q minus W is equals to delta E. But for a stationary system where the mass tak ada keluar in and out, so Q minus W is equals to delta U. And if you have per unit mass, Q minus W delta E, this is per unit mass. So there is various form of the first royal reaction for closed system when we sign convention is used. But when we have flow system, tadi ni close, sekarang we are moving towards a steady flow system. So the steady flow process, okay, is a process during which a fluid flow through a control volume steadily. There is no change in time. Okay. For example, like here, you have a control volume, and there is mass going in. There's also mass going out. So if you know that in order for us to determine the energy from here, M1 multiplied with H1 is equals to M2 plus multiplied with H2 plus M3 multiplied with H3. Then you'll be able to balance the energy in and energy out of the flow. Okay. So during this particular process, it must make sure that the mass of the control volume inside here is constant. The energy within the control volume is constant. The volume of the control energy equals to be constant. Fluid properties remain constant, and power delivered by a system and rate of heat transferred to or from a system remain constant. Okay. Only then be able to use this particular balance lah. We'll be able to make the balance M in equals to M out. So as mentioned earlier, okay, if this particular condition is being met, all of this being met, then we can simply use this particular term, total summation of whatever that is come in is equals to summation of the mass flow rate is going out. Okay, and if let's say you have a single stream, one inlet and one exit, so M1 is equals to M2, and rho 1 V1 A1 is equals to rho 2 V2 A2. So when we revisit back the what we call that energy balance punya equation, right? Because if you imagine that the control volume system again, inside here, the ECB is actually constant. Okay, the energy within the system is constant. So when we write down the energy balance equation, energy in, the rate of energy in minus rate of energy out equals to the change of energy within the system. Because throughout the rate period, the energy of the control volume is maintained. So this is actually equals to zero. So you'll be able to equate that whatever that amount of energy in is actually equals to the rate of energy transfer out by heat, work, and mass. Okay. And if we further substitute the information that we have in order for us to determine what will be the energy, energy can be transferred by heat, work, and mass. So be able to put back this term together. For example, like we have the work, we have the heat transfer, we have the potential energy, kinetic energy, and if you remember about theta, so Q in plus W in plus theta, m multiplied with theta, then you'll be able to get whatever that is going in is the same as whatever that is going out. So from here, this general balance equation kat sini, then we're able to calculate further uh, any information that we need. For example, like if let's say we want to determine certain temperature ke, we want to determine the efficiency, we want to determine the enthalpy, we want to determine the heat transfer, and so on. Okay, so this particular equation is important for us when you later on when you become an engineer. For example, when you become a chemical engineer, um, there will be some leaking, for example, then some problem of leaking, and you want to check, for example, like how much does it leak, for example, okay, and what does it cost to you when it leaks. So first thing first, you need to perform this kind of energy balance. Bila you buat energy balancing, only then you know that, okay, what amount of degree of leaking that you have, where's the source of it, what is the effect to it. Okay, so that's why material energy balance are two important powerful sources for you, so that you can use in order for you to know, to troubleshoot, to design on anything. Okay, so if you want, in what we call as the term used in the equation that I have shared here. Okay, so Q is rate of heat transfer between the control volume and its surrounding. It will be equals to negative, the control volume losing heats, and if let's say Q is equals to 0, then it is fully insulated. Work pula, W is actually equals to power. So W from shaft work, which is turbines, compressor, pumps, and there also W from electrical works, which is electrical wires. And delta H is actually the enthalpy change. So it determines the enthalpy values at inlet and exit from tables. And if let's say it is ideal gas, we can use this equation, delta H equals to Cp T2 over T1. So this is related back to the chapter 4 that I mentioned to you just now. And delta Ke is actually the velocity changes, okay? V2 minus V2 square minus V1 square. If let's say you have two velocity, for example, in the case of you have nozzle, kalau dalam nozzle tu, you have the dua different velocity. So you'll be able to determine what will be the kinetic energy change. And if you're talking about pump, if let's say you put pump and then you have at elevation, kita ada water tank, kita ada sampai ke bawah, and then there is a pump, for example, involved. So you need to know the potential energy as well. So these are the terms that you will be using based on situation. Maksudnya different situation will have a different way of doing it. Okay, different equation that we different. This particular equation is a general equation that we have, but it depends on the situation. Ada setengah situation yang kita boleh omit kinetic energy, ada setengah situation yang kita boleh omit potential energy, but and then ada setengah situation yang kata kita there is no work being done by shaft, or so kita boleh omit that term. So it depends on the scenario, from one equipment to another equipment, from one scenario to another scenario. But in terms of general balance equation, we're going to start with this. Okay, we start with this. When we want to start the general, calculate the energy balance, we start with this term first. Lepas tu baru kita simplify further. If let's say, okay, ada tak potential energy changes? Tak ada. Then we cancel it out. you cancel out. If let's say there is a kinetic energy changes, ada ke tak ada? Kalau ada, maintain the term. Kalau tak ada, kita boleh cancel out. Okay, so that's how we can use this particular term lah, and this is some information about the term itself. Alright, okay. I'm going to talk further later about this lah. Saya rasa I don't want to. I think it's too much information that you already get. It's getting confused. I know confusion is good, but making clear that you make sure that you try to find more information, read more, recap back when you have the video, recap back and try to understand further what this is all about. Okay. But the most important part is you should know that why do we do this is because as I mentioned earlier, kalau you become an engineer, this is one of the skill that is much needed. You really need this, for example, for troubleshoot on something. Okay, you really need the skill. Of course, when you start to work later, you can just use Excel to do calculation. Tapi kalau you tak tahu in terms of the real equation, what is actually coming in and out, that's why actually you will miss out some important figures. I'm sharing with you one example lah. Actually, my sister, the youngest one, she's actually a chemical engineer back in one of the flower punya company, flower, takkan flower, kilang tepung. For the past 10 years, okay, she's the first woman engineer who was hired there. For the past 10 years, the company keep wondering what's going on with the design. Dia rasa macam ada dia punya, there is no, what do you call that? They felt that dia ada missing. Dia masukkan something, dia kata design tak betul. Design of the silo. Silo tu is a place where you put the solid and tepung dalam tu kan. There is a reaction tepung dalam tu. So what she mentioned is that the company keeps thinking that there is some misdesign, there is something missing. Bila they put certain amount, and then after that when they got out from the silo is lesser than what they expected. So what did my sister did is actually she redo back the material balance punya calculation. So when she did back the material balance calculation, she shows here that there is nothing missing. It's just that the calculation they have done, because those who have done the calculation before was not a chemical engineer, was wrong. So there's nothing wrong with that system. Macam itulah. There's nothing wrong with that system. Everything goes perfectly. Okay. So that's why it is important for you to really get to know about the material energy balance, because you will deal with that a lot when you start to work as an engineer later. My sister said right now, even though she's the first lady engineer in that company, now the company hesitated to let her go. Even she feel if she wanted to go, she's already nearly 5 years working over there. So the company treat her lah very well, so that she wouldn't go away. So that's the value of a chemical engineer that you want to be lah, so that you know about all these fundamentals, you know about troubleshooting later on. Bukan sekadar jadi engineer yang ikut-ikutan, okay? But you are strong in the fundamental. That's very important. You will revisit again this particular term again and again from time to time, from different courses to another courses as well. Dia bukan berakhir di sini sahaja, okay? So if let's say you are not that strong fundamentally right now, you still have time to improve yourself, to make yourself better for the future, okay? For the future. Tapi the most important part is your spirit to dig out more information, to find more information, find more resources. That is important. Don't simply depend on me as your lecturer to give you everything, because in the future, okay, this is what I'm going to tell you. because I'm not going to meet you again. This will be probably my last lecture with you. In the future, you will be out there to solve an unknown problems. Okay, whatever that is being taught here is just a fundamental for you. It's just a macam dia macam triggering parts for you to get to know more and try to solve the problem out there. Okay, because kalau problem out there can be solved, of course I can solve that, right? But there are things in the future, whenever that you go outside there is an unknown problem, uh, and the most important part for you is actually to have the right skills. If you know how to find information, if you know how to learn, if you know how to solve the problems, then these are the skills that is needed for you to go out there and solve these unknown problems outside there. But if let's say you are depending on everything just from a single sources, you are expecting that the knowledge only comes from a lecturer, you are not enough actually to be out there to solve the problem outside there, to be someone who are highly valued outside there. So please remember this. Whatever it is, try whatever. For example, just now you share with me your confusion on certain parts here and there. That's okay. Don't wait until you have to dependent on someone to solve or to let you become unconfused, but you solve your own confusion. Find information from you. Okay, I'm going to stop it right now here. um, I'll be doing some kind of video lectures from time to time so that you'll be able to see how does the calculation that you can do. But this is some fundamental for you to understand. There will be some for closed system, you don't have to care much about the about the mass balance because there is no mass transfer in and out. But for control volume, there will be a mass going in and out. There will also be energy going in and out. So the term is a bit more complicated because the energy in and out, it depends not only about the flow in and flow out. It depends on the work that has been done over there. It depends on how you arrange the equipment. If let's say it is arranged at certain elevation, then there is a potential energy. Or for example, if let's say you have a nozzle or diffuser, later on when you look at the slides, on nozzle and diffuser, you have a different kinetic energy because the velocity is changing. So it's no longer similar cross-sectional area. So these are the things that come into the puzzle of solving the energy balance. Okay. Before we leave, right? So this is actually to make up I know that when I look at your quiz, this is also, what do you call that? You need to, somehow the quiz itself tu, the result tu taklah bagus sangat. Okay, so I want you to make up for that, and I would like you to write down your reflection about throughout this 5 to 6 weeks what you have learned on this, and I would like you to spend the next 20 minutes. Please write it down. Okay, what is actually that you feel, what is actually good and bad about this, what can you make the sense of the scenario and so on. Okay, so the link is here. The link is here. You can just type anywhere. So you can start to type the reflection. Please follow the template over there. There are marks for it. Okay, there are marks for it. Dekat sini saya bukan nak minta you all membodek. It's not about that. I just want to know your real reflection about learning thermodynamics for the past 5 to 6 weeks. Okay, and I would like you to follow this template. Write it down based on this template. So at least there is a justified way of for me to give your marks. Kalau ada part that you are missing, you do not write anything from this particular template, maksudnya adalah markah yang terkurang. So here I would like you to write your own feeling, your own thoughts. What do you feel about learning thermodynamics for the past 6 weeks? because this information is very important. I want to pass to Dr. Anis Atika and Dr. Nisa later on to see how much that you actually have grabbed things about thermodynamics itself. Okay, so please spend your time for the next 20 minutes. Please write it down. Write your name and ID as well. Don't forget. So start first with write your name and ID. Lepas tu baru you follow through this particular template. Okay. Please spend your time as well to reflect on the assignment given, on the quiz given to you. Of course, you cannot reflect yet on the test. Okay, by the way, the test, we will give the test next Saturday, not this Saturday, next Saturday, 29th May. Vera is not a mind map, is a essay. It's kind of description essay, okay? It's not a mind map. So the test will be given to you on 29th of May. Okay, 29th of May 2021, 9 p.m. until 11 p.m. That will be the test date, okay?
So just want to clarify, sir.
Yeah.
Just want to clarify that I just put number 1 description and write a paragraph, something like that, right, sir?
Yeah, right, paragraph.
Okay, thank you, sir.
If you find difficulty writing in English, it's okay. I still can accept if you want to write in Malay. Okay, no problem.
Sir,
Yes.
so supposingly for the description, what should we write? Because there it is written that what happened.
What
So
happened
how
lah?
to?
Maksudnya for the past 5 to 6 weeks, what happened? What happened to you?
Oh,
Okay.
okay. All right, sir.
Okay, for those who have completed, you may leave the class. But before that, get ready for the test. Okay, the test is open-ended. Okay, it's an open-ended test, which means that the whenever that you answer the test letter, it can be a different solution, many solution. It depends on your understanding from chapter 1 until chapter 3. Little bit of chapter 4 can be included as well in the answer. No problem with that. Okay, which means that what I'm testing you is your thorough understanding about the concept that you have learned so far. Um, so there'll be calculations in a way that you have to define your own calculation. It is not simply try I give question and then you calculate. Tak ada macam tu. You have to prove yourself with calculation. That's how it's more like a problem solving. Okay. Um, so I hope that you can actually try to master about it lah. So I have to warn you in advance lah, kalau you letak dekat chat pun dia tak akan jumpa this kind of question. Okay. Right. So for those who have actually finished, you can leave the session. Thank you very much. But wait for, I think, 3 to 4 more videos lah that I'll be discussing about the remaining slides. So, okay, some examples that I'll be sharing with you. So, and most importantly, if you have textbook, do some revision with textbook as well. Okay. Coach Shini, I will check. Okay. I'm going to end the session right now. Thank you very much to everyone. Okay, so take care. So I hope that you will continue enjoy learning thermodynamics.
Doctor,
Yeah,
doctor,
yeah.
how to submit because
It's okay. Whatever that you type, later it will appear. I will need to approve that one first.
also just leave it lah.
Just leave it there. It's okay.
Oh, okay. Thank you.
Right? Okay. Thank you. So thank you everyone. Take care. So I hope you nail your test next weekend. Take care. Bye bye.
Thank you, Doctor.
Thank you.
Doctor, so down there it's written that awaiting for approval. So we
Yeah,
just
yeah.
we just
I
leave it.
will approve later. Don't worry.
Okay, thank you, sir.
Okay.